Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on linear algebra chapter elementary transformations, lecture number 1, in which I will give the concept of elementary transformations and elementary matrices. Firstly, with the help of particular examples, I would like to clarify you that what is the elementary transformations or elementary operations of a matrix. We have a matrix A, elements in the first row be 1, 2, 3, in the second row 2, 3, 4, in the third row 3, 4, 5. This is a 3 by 3 matrix. This is the first row, this is the second row, this is the third row. Let we mutually exchange first row and third row. First row is denoted by R1 and third row is denoted by R3. Mutually exchange. This is the denotion. Gives. We write in place of first row elements of third row and in place of third row elements of first row. So this matrix will be of the form 3, 4, 5. Second row remains same position and first row will be in the position of third row 1, 2, 3. Now we mutually interchange the first column and second column. This will be denoted by C1 and C2. C1 and C2. Column change means the elements of second column will be written in the position of the first column 2, 3, 4, and in the position of second column we write elements of first column 1, 2, 3. Third column remains in the same position 3, 4, 5. This is the first kind of transformation, means mutual exchange 2 rows or 2 columns. Second kind of transformation is we multiply any row or any column by a fixed number. Let we multiply row 1 means we multiply elements of the row 1 by a fixed number k r1. Then this type of transformation will be of the form k multiply 1 is k multiply 2 is 2k, k multiply 3 is 3k, and other rows remain same 2, 3, 4, second row, third row 3, 4, 5. Or let we multiply third column C3 by k C3. The matrix will be of the form first column remains same 1, 2, 3. Second column remains same 2, 3, 4. Third column we multiply each element of the third column by k 3k, 4k and 5k. This type of transformation is second kind of elementary transformation. Now we use the third type of transformation. Third type of transformation is we may add with the elements of any row by multiplying a constant quantity with the elements of any other row. Let here we write in the position of second row R2. R2, elements of R2 plus 2 into elements of R1. This type of transformation will of the form. First row remains same, 1, 2, 3. In the position of second row, here elements of second row be 2, 3, 4. With 2, we write 2 plus 2 multiply corresponding element in the first row be 1. Here 3 plus here 2 multiply 2. Here 3. Here 4 plus 2 multiply corresponding element 3 in the first row. Here 3, 4, 5. The third row remains same. Or we may do this type of operation with columns. Let in the position of column 3 we add column 3 plus 4 into column 1, 4C1. The transformation will be of the form. We write column 1, 1, 2, 3, column 2, 2, 3, 4, and in the position of column 3, we write firstly element of column 3 plus 4 multiply corresponding element of first column 1. Next 4 plus 4 multiply corresponding element of the first column 2. Here 5 plus 4 multiply corresponding element of first column 3, and this will be the transformation or operation. Now we define the elementary transformation or elementary operations of a matrix. The definition of elementary transformations or elementary operations on a matrix. Let A, capital A, be a m by n size matrix. Elements are of the form Aij. Let ith row is denoted by Ri. Ith column is denoted by Ci. Then an elementary transformation or elementary operation on a matrix A is an operation of any one of the following types. Number 1 is the interchange of any two rows or any two columns. The interchange of ith and jth rows will be denoted by Ri, double implication Rj, means we interchange ith row and jth row of the matrix. Means in the position of ith row we will write the elements of jth row, and in the position of jth row we write the elements of ith row. And if the column operation is taken into account, then the interchange of ith and jth column will be denoted by Ci double implication Cj, means we write the elements of jth column in the position of ith column. We write elements of ith column in the position of jth column. This is the number 1. Number 2, the multiplication of elements of any row or any column by any non-zero number. The multiplication of the ith row by a non-zero number k will be denoted by Ri implication KRI, means in the place of Ri, ith row, we write k multiply elements of ith row when column operation is taken into account. Then the multiplication of ith column by a non-zero number k will be denoted by Ci implication KCi, means in the place of ith column we write k multiply the elements of ith column. Number 3, the addition of elements of any other row or any other column. The corresponding elements of any other row or any other column multiplied by any number, means addition of k times jth row to the ith row will be denoted by, in the position of ith row Ri, we write elements of ith row Ri plus k multiply elements of jth row. Similarly, the addition of k times of jth column to the ith column will be denoted by Ci implication Ci plus KCj, means in the position of ith column we write elements of ith column plus k multiply elements of jth column. And this is the concept of elementary transformation or elementary operation on a matrix. Now we define elementary matrices. A matrix obtained from a unit matrix by a single elementary transformation is called an elementary matrix or E matrix. E matrix. Single elementary transformation. Firstly, we take the unit matrix. Number 1, unit matrix. Number 2, single elementary transformation. Then the new matrix will be termed as an elementary matrix. Let unit matrix of order 3 is denoted by 1 0 0 0 1 0 0 0 1. This is the unit matrix of order 3. Now we interchange first row and third row R1 and R3. We get a matrix. Let name of this matrix be E13 equal to. We write the elements of third row in the position of first row 0 0 1. Second row remains same 0 1 0. And in the position of third row we write elements of first row 1 0 0. This is an elementary matrix, means single elementary transformation on unit matrix. Let we interchange first column and third column. Here, first column and third column. In the position of first column, we write elements of third column 0, 0, 1. Second column remains same 0, 1, 0. And in the position of third column, we write elements of first column 1, 0, 0. Here we see that this matrix and this matrix be same. So we may write this is E13. Here E13 denotes either interchange of first row and third row or interchange of first column and third column. Same thing. There is no difference of interchanging of row and column. We get the same structure of the matrix. This is number 1. Number 2. We multiply. We multiply row 2 by 3. 3 row 2. So here change is in the second row. We write first row same 1, 0, 0. We multiply the elements of the second row by 3. 0 multiply 3 is 0. 1 multiply 3 is 3. And 0 multiply 3 is 0. Here 0, 0, 1. We denote this by E row 2 multiplication by 3. Now we take C2 in the place of C2, 3 multiply C2. We get the first column same 1, 0, 0. We multiply second column by 3. Here 0 multiply 3, 0. 3 multiply 1, 3. 0 multiply 3 is 0. Here third column same 0, 0, 1. Here we see that this matrix and this matrix be same. So this is also E23. Means we multiply the elements of second column by 3. And if we multiply elements of second row by 3, we get the same result. So this denotation be either operation on rows or operation on columns. Same. This is also an elementary matrix. Now we show the third kind of elementary matrix. Third kind. Now we multiply third row by a number. Let that number be 3. That is, we multiply the third row by 3 and then add with the first row. We denote this R1 is replaced by R1 plus 3 R3. We denote this by E13 first row, third row and multiply by 3. At the place of first row, we add 1 plus 3 multiply the corresponding element in third row, 0. Here 0 plus 3 multiply corresponding element of row 3, 0. Here 0 plus 3 multiply corresponding element of row 3, 1. And other rows remain same, 0, 1, 0. Here 0, 0, 1. And this is equal to, here 3 multiply 0, 0, here 1, here 0, here 3, here 0, 1, 0, here 0, 0, 1. Now we take column operation. C1 at the place of C1, C1 plus 3 C3 means we multiply the elements of column 3 by 3 and then add with first column. 1 plus 3 multiply corresponding element in column 3, 0. Here 0 plus 3 into 0, 0 plus 3 into 1, and other column remains same, 0, 1, 0, 0, 0, 1. This is equal to, here 1, 0, 0, here 0, 1, 0, here 3, 3, 0, 1. Here we see that E133 equal to this, and this matrix and this matrix are not equal. So it is not equal to E133. Now let C3, column number 3, at the position of column number 3, we add 3 multiply column number 1. We get at column 3, column 1 and column 2 remain same, 1, 0, 0, 0, 1, 0. Here column 3, 0 plus 3 multiply C1 means 1, corresponding element 1. Next 0 plus 3 multiply corresponding element 0, 1 plus 3 multiply corresponding element 0, and this is equal to 1, 0, 3, 0, 1, 0, here 0, 0, 1, which is equal to this. So this is equal to E133. Therefore E133 means we add 3 multiply elements of R3 with elements of R1 at the position R1. or we add 3 multiply elements of column 1 with elements of column 3 at the position column 3. So, number 1 elementary matrix is denoted by Eij, which is obtained by interchange of row I and row j, or column ith column and jth column. Number 2 is Eik elementary matrix is obtained by Ri, row ith row is changed into K multiply Ri, or ith column is changed into K multiply ith column. Number 3, Eijk is obtained by Ri. In the place of ith row, we add K multiply elements of jth row, or in the place of jth column, elements of jth column plus K multiply elements of ith column. Here we may see that determinant of Eij elementary matrix is -1, because determinant of unit matrix is 1. Here in this case we have interchanged the 2 rows or 2 columns, and in this case determinant is negative, means -1. Here determinant is K, because we have multiplied 1 row by K and we take determinant, it will be K, because we have multiplied 1 row of the unit matrix by K. Determinant of unit matrix is 1. So, if we multiply 1 row of the unit matrix by K, the determinant will be K. Or if we multiply 1 column of the unit matrix by K and we take determinant, it will be K. And here the determinant will be 1. Eijk, determinant will be 1. Because if we add elements of a row with K multiply elements of another row, the value of the determinant is not changed. That means it will be the value of the determinant, means this determinant will be equal to the determinant of the unit matrix. In 3 cases we see that this is not equal to 0. This is not equal to 0 and this is not equal to 0. Therefore, elementary matrices are non-singular. Their determinant are not equal to 0. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button. And if you have not yet subscribed my YouTube channel, then please subscribe my YouTube channel. Thank you.